Welcome to Super Simple. I'm Marc Teer, the founder of Black Spectacles, and we're recording this session here live from the AIAS Forum Convention. Of course, I'm saying that to everyone here, and they're saying, well, yeah, of course. But we're recording this. This episode of Super Simple. We're recording it. We're going to make it available as a, on iTunes and on our YouTube channel as well. So this is the first time we've ever done one live and in person, which is kind of fun. And you guys are in for a real treat. We have a really cool project to show you guys and some really special people here. This is Andrea from Payette. She's the director of building science, right? And this is Chris Mackey, who's a building scientist from Payette as well. So we have these two really interesting folks who are practicing architecture in kind of a unique way. And they're behind this AIA TAP award-winning project called the Glazing and Winter Comfort Tool, which I think we decided we need to come up with, something like super sexy.
Get like comments in.
Yeah. So if you're listening on iTunes or YouTube later, please put a comment
or shout out at some
for
point.
a sexier name than that. We're open to that. So that's what we're going to talk about today. We're really going to kind of get into how and why they developed this tool and kind of what's come out of it. It's really admirable that they've developed this tool, made it available to the entire profession, and have it. When we get into it, you're gonna see how kind of the benefits that we all get from the work these guys are doing. So it's pretty cool. So first, before we get started, Andrea, Director of Building Science. I don't know what that means. So tell these guys, like on a daily basis, what is it that you do?
Yeah. So my background is in architecture, and I'm a licensed architect, and I was interested in really pushing the issues of building performance. And so I got a post-professional degree in building technology, which is very similar to Chris's background as well. He's both in architecture and building science. And so what we do kind of at Payette in our organization is we spend about half of our time working on project work, really trying to push the issues of building performance. So whether it's looking at energy models or daylight or issues of comfort, but really trying to push the issues of building performance in our projects to deliver better performing buildings. And then the other half of our time we spend working on research projects. So we see the value of trying to understand a problem that we see over and over again in our design work that, you often don't have the ability to kind of solve that problem in the course of a project because of deadlines and other pressures and time. But the firm sees the value of kind of taking that issue and kind of stepping back and spending a little time solving it, understanding it'll pay dividends going forward, that it'll benefit all of our future projects. And so we try to find issues such as this one that we're going to talk about with thermal comfort and glazing in the winter, and try to figure out how we can better understand that to improve our projects.
Cool. So you basically, if I say this back to you, as projects sort of enter the office and begin to kind of move forward, then you kind of hop in and sort of see, okay, is there something here that that we could study, or how does that?
Yeah. So we're actually involved in the projects usually before even pens put to paper. So we're actually often involved in kind of even just going after the project and the initial ideas that we use to kind of try to win the job. Okay. And the idea is that it's sort of baked into how we work and the issues that we consider. And so while there might be someone who's concerned about making sure the envelope doesn't leak, and that's obviously much later than early on. Sure. And as from a technical performance, and there's people that are often concerned more about the design and aesthetic, we're kind of bringing that perspective of performance. So that it's always part of the dialogue and weighed as part of the decisions of if we do this or if we do that, what's going to be the impact on performance. And so it depends on the project what the issue might be. So sometimes it might be issues about energy performance, and that might be the real driver. Mm-hmm. We always care about energy at Payette, and we design generally pretty energy-intensive buildings because we do research labs and hospitals. Mm-hmm. So that's usually a pretty big driver for a lot of what we do. But some clients may not care as much. Sure. But it's often it's a combination of sort of the values we bring to a project, as well as issues that are particular to any given design, as well as the values the client might bring.
And for that case also, we find ourselves doing a lot of comfort and thermal comfort, as you guys will see. I mean, especially, so even when there's not energy stuff to engage.
Right, daylight and radiation. And
daylight, glare, all these sorts of issues that come into, that everybody is on board with, that we know we want to make a good occupant experience.
Yeah, because the nice thing about sustainability is there's a lot of benefits, and so I just start talking about the aspect that they care about once you kind of figure out what motivates the client.
Yeah.
So you can still talk about the same strategies, but you talk about it from the comfort perspective
Sure,
rather
sure,
than
sure.
energy.
Yeah. Okay. Cool. And so, so then, Chris, a little bit about you. I don't know. You sort of had a hand in this tool. Maybe you guys have heard of it, called Ladybug, which of course is a really powerful plug-in, I guess, to Grasshopper. So to set it another way, that's one of the developers of Ladybug. So if you know what that is, that's kind of cool. So tell us. So that being said, you were studying in school.
Yep.
How did you get in? How did you get in this Ladybug thing, and how'd that come to be?
So I was studying, I also have a background in architecture, and I did a dual degree with building technology at MIT, just as Andrea had done. And as I was doing that, I had an internship with Mustafa Rudsari, who's the guy who started the Ladybug project. And I saw, I was starting an internship over the summer while he was starting to work at the same place as I did. And I saw what he was doing after struggling through a few different types of tools. And I just knew that this was the thing that I wanted to apply to all my projects. And I didn't know how to code at all at the time. I didn't know anything about software development. But in the course of like a year and a half, just by applying this to my school projects and applying it to a few things, a few real projects that I eventually taught myself, or rather used the community to help teach myself, and all the examples that are in there. And now, after a year and a half, I had committed 50% of the Ladybug code, and now the project's growing. We're getting more developers, and we've got I think 20 people who have committed code, who have added code, and I think we're at 55,000 downloads. So.
That's awesome. Very cool. All right, good. Well,
and we applied, of course, a lot at Payette too. So
there you go.
And you actually get to see a little of that today. That we have a tool that one of the versions of the glazing and comfort tool is a Grasshopper version built with Ladybug.
Yep. Cool. All right. Well, that's a perfect transition. So let's go ahead and hop in, Andrea. So this is. Help me understand a little bit the problem you guys were sort of contemplating here.
Yeah, so we wanted to build better building envelopes. It leads to lower energy and more comfortable spaces, increased occupant satisfaction. And so that was really the driver for a lot of the research projects that we do are often focused around envelopes, because it's one of the nexus of where architecture really informs building performance. And so this was one of such ones.
Mm-hmm.
And we were particularly looking at comfort and how building envelopes can impact comfort. And so just before we kind of delve into our tool, we thought we'd go through a little bit of basics, just in case anyone had a studio project and fell asleep the day that you covered the HVAC systems in school, or haven't gotten to the class yet since you're all in school still. So just as a review, there's kind of 3 modes of heat transfer. There's conduction, which is when the air moves. So we kind of feel that air movement.
Convection.
Oh, sorry, convection. Sorry. Sorry, convection. Good thing Chris is here.
They sound very similar.
They do, yeah. Conduction when you touch something hot. So there's through that direct connection, and then radiation, which is through the infrared waves. So right now, I'm radiating to you, and you guys are radiating to me, and we're kind of exchanging heat.
We're all glowing.
Exactly. And so it's based on sort of, and that's like if you sit near a hot fire, you kind of feel that radiation, or stand in the sun. Is another good example.
Okay.
And so everything that we know about thermal comfort has really come out of some studies that were done by this man named Fanger in the 60s at the University of Kansas. And it was really based off of kind of what was considered typical office workers in the 60s in Kansas, which were kind of these farm-fed Midwesterners in their 3-piece suit.
And to this day, I mean, the unit that we use to measure clothing, we have 1 klo, and it's a 3-piece suit.
Yeah.
It's equivalent to a 3-piece suit. Huh. And so it's still a very much so what gets used a lot.
Yeah, and so today, and for today's office environment, we have a lot of women. We have office snuggies to accommodate that, because how we think about comfort isn't really has not been really adapted to the way we work today and the different environments that we have. So there's been a lot of current debate in the news about why are our buildings so cold? Is it sexist? And what about? And so this is one of the issues that we became really interested in comfort, and it's, I think, a very relevant topic currently in the industry today.
Mm-hmm. By the way, there's one nice article in that there, which is showing we have one of our coworkers in a Snuggie which is the equivalent of a three-piece suit in
Yes.
terms of clothing insulation. So that's just to put things in perspective.
Okay.
So there's basically 6 factors that we use to quantify thermal comfort. There's the metabolic rate, which is what you're doing. So whether you're sitting and reading a book versus running laps around the track, you feel comfortable at very different temperatures. How much you're wearing. So if I were sitting here in my shorts and t-shirt or my snowsuit, I would feel very comfortable at very different temperatures. There's the air temperature, which is what we all think of when we think about comfort, sort of what your thermostat reads. There's the mean radiant temperature, which is the average temperature of all the surfaces you're seeing. So if you're sitting next to something really hot or really cold, you're going to notice that. Airspeed, so if I were sitting under a fan, I would feel comfortable on a hot day, but might feel cold on a colder day. And then the humidity, right? On a hot and humid day, you notice that. But there's really 4 of those factors that are influenced by design. So we can't really control what people are doing or wearing in our buildings. At least I can't. Maybe you guys have more power someday. But right now, we don't really control what people are doing in our buildings. And then, what we only really measure is one thing, is airspeed, or air temperature, sorry. And so the problem is that we have one metric that we really use to try to understand comfort when it's really affected by many of these different factors. And then how we translate that, how we can kind of translate that into understanding whether or not people will be comfortable or not, is there's two kind of versions that we use to quantify how people feel. So one's called the predicted mean vote, abbreviated PMV. And that's if we were to take a survey right now in the room and ask how many people are perfectly comfortable, and you'd say, some people would raise their hand, and that would be a 0. And then on a scale of like 1 to 3, from being really slightly cool to cold, to really cold, it would be -3 being very cold and +3 being very hot. And that's kind of the predicted mean vote. And that translates into, you can take that survey and you can translate the predicted mean vote into what's called the percentage of people dissatisfied, which is the PPD. They really like acronyms when they talk about comfort.
Okay.
and yeah, the reason why it's a mean vote is because you've asked, like, let's say 100 people how they feel. Do you feel hot or cold? And then you say you average those all together, you get the mean of that. And that's where you're able to say, over those 100 people, this percentage are not happy.
Right.
Too. It's meant to be over a population, not just for an individual.
And because we can never satisfy everyone, I'm pretty much only comfortable at the temperatures my husband's hot at. So there's not really a Venn diagram of the temperatures at which we're both hot at, or both comfortable at. There's an assumption that you really can never get better than, you can't get to 0%. You're never going to have everybody completely satisfied. And so what we do is we have different thresholds that we consider acceptable for thermal comfort. And the industry standards are usually 10% or 20%, depending on how stringent you kind of want to be in those comfort thresholds.
And that's 10%.
Dissatisfied.
Dissatisfied.
Yeah.
Okay.
Yeah,
And
we want more than 10% dissatisfied.
But then the scary thing is also that a lot of our buildings, or at least when looking at a number of real buildings, will be on average somewhere at like 30 or 40% over the industry.
Dissatisfied.
Dissatisfied. So a lot of the times we're not even meeting these goals that we set.
Okay. Okay.
Just because we're not aware of them, or because we're only focused on that air temperature and not everything else.
Okay. I mean, folks in the audience, raise your hand if you're normally cold or hot in school or work. Raise your hand if you're normally cold or hot. Right? Like that's almost everybody, right?
Yeah, that's
Yeah.
probably at least 50%.
That's interesting. Good point. Okay. Cool.
So, back to building envelopes and why I think you guys came. Or maybe it was just Mark.
No, it's you guys. Sure.
So we were interested in trying to understand, particularly related to glazing, because we work here in Boston. We do work all over the country, but we do a lot of work in the Northeast. And windows are a big source of discomfort in the winter. So you can go to the next slide. So there's 2 main ways that glazing impacts comfort. One is from that radiant temperature. Because it has a lower U value, it's much cooler. And so we lose a lot more heat to that glass than we would to an exterior wall. And then there's also something that's called downdraft that happens where there's a draft that comes off the window.
And so the important thing is that the radiant temperature that's over your whole body, you're going to be feeling cold. Whereas the draft is more like a local, like your ankles are feeling cold, or your hands may feel cold if it's on a desk or something. So they're 2 kind of different types of comfort too.
Yeah.
Okay.
So for the radiant comfort, there's 2 factors that impact that. So one is the U value of your glass. So how much heat are you losing through your glass? So if you have a really good triple pane piece of glass, it's going to be a much warmer interior temperature. And you'll lose less heat to it because there's a lower delta T.
3.
Yeah.
Triple.
Exactly. And the other is what we call the view factor. So the view factor is how much your body is seeing that glass. So if it's a really big window and you're standing really close to it, like say your studio desk is right next to a really big floor-to-ceiling piece of glass, you're going to have a very big view factor to that piece of glass. If you're in an old building that has kind of punched windows and you're three desks in, you're going to have a very small view factor to that glass because it's a very small percentage of what you're seeing. So the smaller the window is, the further away you are will impact whether or not it will make you uncomfortable, in addition to the temperature. And then for the downdraft, there's 3 factors that impact the downdraft. And basically what happens with the downdraft is warm air is typically delivered in the, around the ceiling, or it's in the, closer to the top of the room. And it hits the glass, and cool air falls, and natural convection. And so it falls down the surface of the glass, and as it kind of continues to cool, it picks up more and more speed. So the temperature of glass influences how big that draft will be, because the cooler it is, the more it's going to cool down and the faster it's going to go. The taller the glass is, the more it's going to kind of continue to pick up that speed and have that draft. And then how far you are from the glass is going to impact whether or not you feel that draft. So again, if I'm 15 feet away from that piece of glass, I'm not going to feel that draft. It's going to have dissipated in the room. So it's really only if you're, the closer you are to it, the more you're going to feel it. And so what we do typically in a traditional design, in most projects that are in the north of our country, is we put in a perimeter heating system. So it's often radiant heating or something like that. Yeah, exactly. To warm up that glass, to try to counterbalance that radiant temperature loss as well as the cool draft that's coming off of that. And so it's a supplemental heating system. We have heat that's delivered, into the, whether it's a VAV system or whatever the mechanical system is for space, we have heat that's delivered to keep the space comfortable. But that perimeter heating system is really just to keep the glass warm so that we're not to keep the space comfortable. And it also has the sort of, adding a perimeter heating system uses more energy because we're now running a separate system, but it also actually degrades the performance of our glass. So it lowers the U value by heating up that glass and minimizing the air film.
It's really if there's a least efficient spot to locate heating within your building, it's right at the window where you're losing it. So like so much heat is just being thrown out the window because we put it right next to it. So there's a lot to be saved that if we could find some way to remove that.
And so I think just to give you guys sort of where we're going here, I mean this point here about the supplemental heating that's at the window. I mean, if you want to design a building that's all glass or that has lots of glass in it, then you end up, when you really make the building, you end up at this point where you're like, oh man, we got this glass. Man, it's going to be cold. Okay, we have to put in this this radiant supplemental heating system, which, as you just said, super inefficient, so it wastes a bunch of energy, plus it's also expensive, right?
Yep.
Yep.
And I had no idea that it also reduces the U value of your glass.
Yeah.
Yeah.
Over time, or just whenever it's on?
Whenever it's on.
Whenever it's on, yeah. And the thing is that it kind of, because you're heating up that glass, you're removing kind of the resistance you get from the air.
Got it.
In front of that, between the surface.
Okay. You guys really did study building science.
Yeah. Yeah, hopefully we live up to our titles.
Good enough.
But, so one of the things that I noticed as a practitioner working was that sometimes we were able to get rid of the radiant heat, whether it was because the windows were small enough or we did things like going to triple glazing. And so I started to ask some of the engineers that I was working with and other people, so what is that threshold? Like, how do I, because one of the interesting things that I was noticing was that when we were able to actually get to that threshold where our design was comfortable enough that we didn't need the perimeter heating, as you said, it's expensive, we could actually, it was actually cheaper to put in higher performing glazing. So I could afford triple glazing if I didn't have to have the perimeter heating. That's actually a cheaper solution than to put in this supplemental system. So you end up with a better building that costs less and is going to operate.
And just like for an order of magnitude of like the statistics we found on one of our projects, that we found that we could put in an extra pane of glass to make it go from double to triple, and that would eliminate our need for perimeter heat. The cost of the extra pane of glass was about 1/10 of that of the perimeter heating system. In this case.
Hold on, you said the cost of the glass was
to add the extra pane in to change it from double to triple was far less than the perimeter heating. I mean, and granted, this was a project where we were using European glass it was easier to go to triple pane, but it's still on almost all of our projects we can.
Yeah, for every project where we've been
savings.
able to kind of cross that threshold, we found it's cheaper. The problem is we weren't exactly sure where that threshold was. Like, when was our glass comfortable that we could make the case that we could eliminate perimeter heating?
Okay. Okay, so it all came back to comfort, which is why we
Yes,
went down that road.
exactly.
It's about comfort
Yep.
and like how do you,
Yep.
and so what you're saying is that there was some question, you weren't sure
Yeah,
if the design you were making was going to result in
exactly.
the optimal levels of comfort. And so you had this surefire win. We can save you all this money. We're just going to throw another pane of glass on there, and then we're going to get rid of this this perimeter heating system. But we're not really sure if we're going to make everybody mad because
Right.
they're going to be uncomfortable.
And when we talked to different engineers, they kind of had different responses of when it was comfortable and when they would be willing, because they own the supplemental heating system, when they would be willing to get rid of it.
Right.
So I had one engineer tell me when I asked them that they would do it when the U value of the glass is the same as the U value of the wall, which you guys probably aren't specifying glazing yet, but that doesn't exist. So
Yeah,
it was kind
it'd
of
be
like
some fancy aerogel,
Yeah.
quadruple pane, something.
so it was kind of like, okay, that doesn't seem like the right answer. What else could it be? And so that was where we embarked. We decided, well, this seems like a good issue to understand better because it'll benefit our projects, it'll benefit our practice. We'll be able to kind of always design facades that are comfortable and not have to have the supplemental system.
Okay.
And we
so-
can just have simpler, like sleeker designs that don't have this extra system. in it.
Right, which
It's just have
we
the
like
window.
the aesthetics of better.
Yep.
too.
Yep.
It's really a
Okay.
win-win all around.
Okay. So the goal here is how do we eliminate the perimeter heating? You already know that if you do, you're going to save a lot of money, but you're trying to figure out if everyone's going to be comfortable when you do
Yeah.
it.
And so this is this is just trying to map out how we were trying to change our design process around this. So in the traditional design, we would do the geometry of the glass and the building kind of based on aesthetics and whatever else were driving that decision. And then we might go and say, okay, code says this is what the U value needs to be for the glass, and we're going to be better, so we'll just kind of up it or whatever it might be. But we'd sort of pick it based off of, not really informed based on comfort, let's just say, based on other reasons. And then when it came to value engineering, if that happened and they tried to say, well, triple glazing costs a lot of money, so let's go to double glazing and it'll be cheaper. And we just put in the permanent heating system, and it was kind of it wasn't integrated.
I'll just pause for a moment.
Yeah.
You guys would be surprised, when I practiced, in my career at Gensler and so on, you'd be surprised how many decisions about putting a building together are just kind of like, I don't know, we did it on the last project. Like, what?
Yeah.
Like, where's the actual data and information that sort of proves that this is the right thing to do? And there's this, I don't know, there's this old-fashionedness about making buildings. That it's like, well, what did you do in the last one? Well, and if you want to do something different than what you did in the last 2 or 3 buildings, like, wait, what are you talking about, So that's when you really do need to prove that you're not,
Yeah, I mean, and
Full
that's
nonsense.
something that our whole industry, because our buildings are expected to last a long time, they're expected to be these things used by a lot of people. We are very adverse to change as an industry, and that's why people say the building industry moves so slow, and it's very hard to move things. But that's also the reason why tools and simulations and research, why this is one of the most effective ways to make change. Because if you can prove something works before you make the building,
Yep.
you can start to have enormous impacts on what happens.
And you're teeing up these transitions. It's really good.
And I always say that the building envelope is one of the most important things to invest in up front, because you might go through and replace the lighting system in 10 years, you might change the HVAC system in 20 or 30 years, but you're not going to take off that facade and replace it, maybe ever, but certainly for probably 50 years. So investing in making sure we don't value engineer what we need from the performance of that facade is really critical.
Oh, that's a really great statement right there.
Um,
Everybody should just take that and write that down, record it, play it the next time you're presenting your project to a client.
And so, so we wanted to try to create a tool, as I said. We started off with a goal. I am not as technically savvy as Chris, and so I started off with the goal of wanting to make a chart in Excel. And trying to take these kind of 5 factors that we talked about that looked at both radiant discomfort and downdraft, and trying to combine them into one chart that I could then reference to say, my design is going to be okay. And so this project actually started just about 3 years ago now, actually in 2014. We had a little bit of a slow time, and so one of the another building scientist and one of the staff and I kind of started delving into this and trying to figure out how we could approach this. And so we came up with an Excel chart. Then we looked at how. Then we started getting a lot of. There's a new technology called room side low E that came out that we started actually getting as a value engineering alternate to a lot of our triple glazing. So we kind of added in researching that as part of our research project. And then at a certain point, we decided we really needed something that was a little more dynamic. So we ended up with the Grasshopper tool and the online tool that's had a few different versions that we're going to talk a little bit more about.
Yeah, and this timeline is kind of just showing that there were also a lot of publications along the way, a lot of presentations of this. And I mean, also on there when like the 6 people that are on the project, when each of them sort of came in, and you see I'm at the end there.
Okay.
Yeah, so it's a group effort. Chris and I are here representing, the work of many.
Very good. Okay.
And so the idea for kind of this tool, we wanted to like not just have it be one person's tool that sits on their one machine. So we wanted to make sure that a lot of groups were involved. And so we definitely, as building scientists, we did a lot of research into the existing standards, into existing papers and publications on what had been done to research this topic, which was very necessary. But we were also very sure to try and engage the design community, the architects. And also us having architecture backgrounds, knowing what are all the capabilities, all the types of facades that we need to simulate. And finally also bringing in people who, well, including myself, who know scripting and coding and interface development. And so each one of those things was kind of brought together in bringing not just knowledge from different parts of, from different disciplines, but also, bringing skills kind of into one tool and different aspects of that tool.
Yeah, and I just, as a kind of a bit of a plug, this was all developed in-house. And so I think one of the things that we did a pretty good job of is trying to figure out the different skills in-house. So there was someone that happened to be really interested in web design and really good at kind of D3, tapping into Chris and some of his abilities, tapping into the building scientist's ability. We had a couple architects working on it who deal with design and kind of how they think that would integrate into the design process. And so kind of the conglomeration of the different viewpoints that everyone could bring, I think, is really what made it a useful tool. It's if we only had one of those perspectives, I think it would have lacked.
Yeah, and certainly there are many examples of tools out there where it was just the one person with their one perspective, and it's important. That's also why we keep the tool open, because we want this to be a dialogue.
Yeah, so this is a part where we're going to sort of jump in, and we're going to get into the guts of how these guys developed this glazing and comfort.
Winter comfort.
Winter comfort.
Yeah, because we don't look at solar radiation in the summer
I
and some
know,
of those
yeah,
issues. That's our next tool.
GSCDT. I don't know. That's terrible. I'm bad at names, so I'm not the right guy. But anyways, so here's what's interesting. I mean, if you know, I don't know how many architecture firms you've worked at before or what your experiences are, but the fact that, here's a firm who has a research arm. What? Architecture firms don't have research arms. So here's a firm that has a research group. You told me a little bit about how your research group works.
Yeah.
You mentioned that it was primarily yourself, but that what you guys do is you sort of lead the research efforts among the staff. So actually the people who are doing the work and figuring out this research and kind of doing the studying and doing the iterations and whatever.
It's not me.
It's not you, it's the people, it's the good old architects who are doing it, right? And then as you just mentioned, I just want to highlight this point. So I could certainly name some firms who, sure, they do have research groups and they keep all their stuff in-house. So they have their little research team and they develop their little tool or they develop their little script or whatever, and then they just share it internally and that's it. And they do that because they consider maybe that's their competitive advantage. So actually, can you comment on that topic?
But well, I think I get the sense, and actually I can even, maybe the most honest way to comment on it is to say that there was also that mentality in Payette at first, when we first came out with the tool. And it took some convincing of the heads, all the principals that we really are going to see the benefits of this.
Well, there's a diverse view set.
Yeah, there's a diverse view set,
Yes.
yeah.
But not everyone was on board.
But that's very much so changing now, and it's definitely changed in Payette. I know we're seeing a lot of benefits from the tool, and I think it's changing industry wide too. I've seen other offices now slowly, at least, starting to realize that we have much more to benefit by putting everything together and validating one another's tools, or we may have one piece of the puzzle and someone else may have another piece of the puzzle, and putting those together. Rather than just keeping all of our individual tips to ourselves.
So tell me a little bit more about that. We talked a little bit about this on the phone prior to this. Some of the benefits that you guys see, just the straight up, what do you guys get out of making this available for everybody, anyone to use?
I think there's a couple benefits. I think ultimately our goal is to advance the industry.
Sure.
And if we all want to advance the industry, we need to share our best knowledge and how to do that, because I'm going to benefit from someone else's tool, and if they keep it private, I'm not going to get to benefit from it. So I think we see the value in sharing it so that we can all kind of advance together. There's certainly a marketing benefit. I mean, if we hadn't made it public, we wouldn't be sitting here with you today,
Right.
and you wouldn't all be listening about our tool. So we're getting a bit of PR from making it public and having ourselves associated with being expertise in a certain topic.
Yep.
And I think,
And we're also, I mean, maybe just, we'll
Yeah.
show this example in the tool itself, but as an example, the scientists, these brilliant scientists over at Berkeley, are
Right.
redeveloping the comfort models right now that we use to evaluate the draft, that discomfort at foot level. And they have a much more accurate model that describes our case much more perfectly. But it's not, they haven't published everything yet. But the fact that we made our tool open and that they could see the stuff that we've done, that we're sharing our iterations with them, they've shared their model with us, that we're able to collaborate much more easily because we were open with this to the start.
Right.
And because they were also of this open mindset, that there are benefits. I mean, it will all around be a much better tool, a much better workflow, and if we share this stuff.
And I could imagine the counter argument is, oh well, if we didn't share it, or if you didn't share it, then you guys would have that expertise. You could go to Marc and say, oh, we're smarter than everybody else, right? But actually, that's what you're doing by sharing it.
Yeah.
You're saying, oh, look,
Yeah.
we're smarter than everybody else. So it's actually sort of the same thing,
there's
but you're getting
also-
the benefits of other research and plugging into other things, right?
Yeah.
And there's also a bit of an awareness issue. So we have all of our research on our website, and the other big research project that we've done is we got a grant from the AIA to look at thermal bridging. And thermal bridging is a really big issue in terms of building envelope performance. But if we just keep saying, well, we're experts in building envelope performance, but nobody's talking about thermal bridging and thermal comfort, like nobody knows it's an issue to care about. So you almost have to build the demand for why people should care about it, which requires you to kind of share and talk about what you're learning.
And you're bringing up, I think, another point here. There's a big difference between just saying that you're smart and proving that you're smart. And it's that validation from other peers who look at your tool and other experts who say this is a good thing to use.
Yeah, when you have a smart client who's like, oh wow, these guys claim to be really smart, let's go see. Then you go, and you find that public research or publicly available research. So needless to say, I think part of the spirit of this whole super simple idea is to sort of share ideas because it advances the profession. And
Absolutely.
so that's why I want to sort of drill in the point that there's actually really great benefits for doing that.
Yeah.
So we sort of paused here on the evolution of these tools, which we talked a little bit about. Do you guys want to comment on?
So yeah, I mean, this kind of parallels the timeline that we showed previously.
Okay.
Sure. I mean, as I said, we started off with this kind of hybrid Excel tool and utilizing the Berkeley Center for Built Environment. They have a tool for kind of looking at thermal comfort, and we were sort of using those in conjunction. Then Chris created a Grasshopper tool.
Very hacky one.
Very hacky one, but that was kind of working. And that was really part of what led us to think, well, we really need something that's more of a graphic interface than just our Excel tool, which was doing an okay job, but really needed something a bit more. So we created a web tool that we put up on our website and made available to everyone. And then from that, we learned things like Chris mentioned, that there was a better way to look at downdraft than what we had originally known. And we could probably improve our Grasshopper tool. And so we've come up kind of with a 2.0 version of both of those.
Okay.
And so, so we're going to walk through at least what those individual parts were and some like the struggles, how we decided to move to the next stage and stuff. But the first tool was kind of what Andrea described in the beginning, like a chart of just, if I have my window U value on my y-axis and my glazing ratio on my x-axis, can I find a point on this chart that makes me happy? And can I use this as like a way to find what's going to be comfortable for a given project? And while this, it was certainly useful on several projects, it kind of can start to break down once you start having different glazing types that may not fit on this chart, or different facade designs, or different sort of outdoor temperatures. And also another thing, if you go to the next slide, it was relying on this kind of hybrid of you had to plug in stuff in Excel to generate the chart first. And then at a certain point, you had to manually go over and plug in individual values in the Center for the Built Environment's web tool, and then bring those back over to the Excel. So it was a long process to generate one of these charts. And
if you go back a slide, just to kind of explain the chart. So, Chris did a good job, but it's actually view factor on the bottom. We started off with the goal of wanting to have it as % glazing, but because it's based on view factor, it wasn't really easy to do that way. And so we had to kind of come up with these, like, well, if you're a punched window, it's this kind of column. If it's a ribbon window, these are some examples. And if you're fully height glazing, it's over here. And then those kind of swoopy curves, those are the thresholds at different outdoor temperatures, and so we needed different ones of those depending on different climates. And so it started to become a very multifaceted problem that wasn't really easily translated into an Excel chart.
Okay.
But amazingly, the one thing that this tool did do, which was surprising, is that it did all the geometric calculations in an Excel interface, which is just something that I thought was really impressive for Excel.
Yeah.
And actually, for all the knocking of Excel that I do, it's like it's probably still the most widely used like BIM tool in the industry, just because everybody knows it.
Yeah. Yeah.
But so after that, I mean, once I got the chance to look at least all the formulas and stuff under the hood, is that I hacked together in like a couple of days a Grasshopper version of this. And the nice thing about this was that it at least had everything in one place. You know, that you didn't have to run over to the CBE tool, but it was very hacky, and at least I mean you could change the glazing ratios, but we really hadn't come up with that good of an interface yet. We were still sort of looking at you know, what U value do you need at a certain distance, and it was maybe a little bit confusing if you have U value on the y-axis and then distance from the facade on the x-axis. But at least it gave us these visualizations. It gave us a little more freedom to play around with different things in a bit faster way. But it definitely was still going to be something that lived on my machine that wasn't going to be used by a lot of people. I mean, there's a picture of the Grasshopper canvas up now. And this is, I mean, as you can kind of see, like most Grasshopper canvases, it's a mess. It's like not very clear to you know, understand how things are working. And even though we tried to organize it with these like bars and stuff, you know, it's a hack. It was, you know.
And do you guys work a lot in Grasshopper or no?
Is there any Grasshopper people here? Don't be shy. Okay, all right.
All right.
Yeah,
So, like
it's-
the rest of you are candidates for some Black Spectacles tutorials. Shameless plug. Nice job. Thank you.
No problem.
That's funny.
But so after we had the kind of Grasshopper tool, and you know, at least had something we can iterate through, we realized that we need to have something that we could like share, something that's like usable, something that is simple enough. You know, combining some of like the simple geometric calculations maybe of the Excel tool with the other things that were faster on the Grasshopper tool.
So were you able to plug in? You talked about this other maybe sound like a database or something that you were connecting to. This thing here, the CBE.
The CBE tool.
Yeah.
So with this Grasshopper definition, were you connected to that as well?
So the thing is that we were using the Ladybug components, which actually, so we were using the function to calculate human full body comfort is a really complex one because, not to get too nerdy here, but it has to do something called an energy balance, which involves iterating several times until you're at a comfortable temperature. So if you imagine I go into a hot room, it's going to take an hour or so for me to warm up and actually feel how comfortable I am in there. And so that's what this comfort model does, is that it runs, you know, for each and every minute, keeps running balance until it figures out are you comfortable or not.
Okay.
And so that's a really complex, I mean, it's something you really can't do in Excel unless you use their scripting interfaces. And that's why we were jumping over to the Center for the Built Environments tool to do that calculation for us, because they had that pretty intense one there. But with Ladybug, I mean, I had actually taken 2 years ago, taken that CBE tools function and put it into a component in Grasshopper so that we can now easily do that all within the interface.
So you were doing the calculations within that
Python component, yeah.
Okay.
So that's why everything can be in one place. We can iterate fast. You don't have to jump over to the Center for the Built Environments tool.
Okay.
And just in case anyone doesn't know Ladybug, Ladybug is a plugin for Grasshopper that allows you to do climate analysis and comfort and other analysis, just in case you aren't familiar.
Yep. And energy, and there's an insect honeybee that does energy analysis and daylight analysis. And sorry, that was a shameless plug. And so after kind of playing around with the Grasshopper tool, we came to the web tool, which is the first thing that we really felt that we could share. We could have other people in the office use it, like, you know, that it was fast. And we spent a long time developing this too, and trying out a lot of different iterations, different interfaces. It definitely took me, a lot of playing around on the background because this was the first time I was coding in JavaScript. But the payoff, I mean, it really seemed to pay off where you had an interface in the upper left where you can do any kind of orthogonal or rectangular facade. I can say orthogonal. We've got architects here. I know. And then it's got a graph that's showing you as you get further away from the facade, what is your discomfort, and then on the right side, it's got a panel of inputs that you can easily click through and test. You can do several cases to compare different designs to one another, and it's fast enough that you can really come up with general strategies for how you're going to remove perimeter heat. You can use it that early in design to be able to.
So here's the thing. So we were trying to figure out, you needed some way to prove that you could achieve the appropriate comfort level with your design that didn't have the perimeter heating.
Yep.
So this doesn't have there's no available perimeter heating button here.
Nope.
Where you can add the perimeter
Well,
heating.
the idea is that so that chart that's kind of on the lower left, there's
This
a
guy.
gray line.
This one?
Yeah,
Yeah.
that chart. So there's like a black line across the top. That's the threshold of comfort. And you can kind of define what that threshold is. I think here it looks
guy?
like we defined it as
Yeah,
10%. Yeah, exactly, that
horizontal
guy.
line.
Yeah, sorry, the horizontal line. So that line there is the threshold of comfortable. So if your design is above that, then you're going to need perimeter heating. If it's below that, then you don't. So the idea is that line is kind of telling you if your design is kind of hovering above that,
Yep.
then you're going to need that supplemental
So, but I
heating.
guess the question, so I'm going to guess that this point is like your face is on the glass.
Yes.
Yep.
And then this is you're a foot or 2 feet away from the
Yep,
glass.
that's 2 feet.
So in this case, these three designs aren't really compliant, or
Right.
because if you're 2 feet away, you're uncomfortable. and
Well,
that's
so
not-
you
that's
have
not
the
gonna-
ability, there's a couple sliders up
Yep.
here.
Yeah.
So one of them allows you, the top slider there allows you, those ones. The top slider allows you to set your threshold for comfort. So you can say, I want no more than 20 people dissatisfied, 10 people, whatever that threshold might be. So you can slide that and
So
choose
here
for
you've
yourself.
got it at 10%. It looks
Yeah,
like,
we have
right?
it at 10%.
Which
So
is
it's
what
at
we
a
were talking
slightly
about
more.
earlier.
Yeah, exactly.
And that again, just going back, that 10% is who came up with that? That's
Fanger.
okay.
The guy
Not even Fanger. This
Oh,
was
is it? Oh, I thought it was.
ASHRAE.
Oh,
This was
okay.
a group of engineers who just said, that sounds good.
Yeah,
So if
And
10% of the people are pissed off,
that's
okay.
as good as we're going to get.
Get out of here.
yeah,
Go get a
yeah.
Snuggie.
Um,
Okay. And you guys
yeah.
set it, in this case, you set it to that.
So this one we set it at 10%, and then the lower one allows you to set where in the room you're concerned about. So we have it set right here at that dotted line, which is 3 feet. So we're saying the closest occupant to that glass is going to be 3 feet. That's where their desk is, or
I see.
whatever it is.
So going back to, let's say, this image here, where you've got someone sitting
yeah,
on the glass.
that would be, you
okay.
might have that
Maybe
at a
that's a
foot and a half to 2
right.
feet. Yeah, exactly.
Whereas that's maybe the same thing.
Same
That's
thing,
maybe,
but yeah.
but if you had nothing there, maybe this one here, this one,
Yeah.
where you have nobody along the glass, okay, fine. Well,
Right.
there's no seating there, so fine, it could be 4 feet or something like that.
Mm-hmm.
Yep.
In which case, you need, this would be okay.
Yep.
Because it looks like at about 3 feet, at least this one design is
Yep.
below.
Yep.
Okay.
And the
then
other
these
two
are all, as you
comfortable.
said, these are all little toggles
Those are the
here.
inputs. Yep.
And then this is case 1, case 2, and case 3.
Yep.
So you can study those 3 things.
Yep.
Okay, got it. Cool.
Yep.
And we were going to go through a tutorial later, but
Yeah, we'll do a demo, assuming, we
Yeah.
already got it up, so
Yeah.
we should be good.
Yeah.
And there were a lot of other sort of extra bells and whistles that we added on here, explanations for like what was driving the discomfort, or whether it was radiant or downdraft. We had a bunch
so
of
there's different
advanced
shapes
Yeah.
for the little markers and the curves. So you'll know whether or not it's being driven on this version. You'll know whether or not it's being driven by the downdraft or the radiant discomfort, so you can try to understand what you need to do to solve the problem, hopefully. And there's a down in the corner down here, we have little explanations on what radiant discomfort and downdraft are, so you can kind of
And again, the
learn
thing
a bit
that
more.
the architect is playing with, of course, it's really small here, but
Yeah.
are the characteristics of the
Yep.
glass, right?
Yep.
So what the U values are.
Geometry and the characteristics of the glass.
Okay, so the architect can change the size of the glass, and then the things go down. They can they can improve the performance of the glass, and the bar goes down even further. Those sorts of things. And again, those are choices that architects have been making for many, many years. Not a big deal. But the big deal is that now we have a way to visualize that. sort of
And now it's
and-
informed on how that impacts comfort. Because we make those decisions, but we didn't have
Right.
the information on how that would impact comfort
Yep.
before.
Okay, cool.
or the decision to put in perimeter heat
Right.
later. You would just accept it.
Yep.
Whatever our
Yeah.
engineer said, and they just typically are conservative because they assume we're going to lose at some point.
Okay. Has this whole thing been vetted by engineers, the people who were kind
Yeah, we have engineering
we were
firms
kind
that
of
are
very
actually.
subtly dogging them?
Yeah, I know. Sorry for any engineers listening. Yeah, we actually have a few firms, engineering firms, that have been using it.
Oh, okay. Awesome. Okay.
Yeah.
So then you moved to this.
And so, yeah, so after we had that initial web tool, we sort of came back, or at least we came back to the Grasshopper tool to say, now that we have a good interface, we know we can share it, we know it can give us quick information early in design, well, actually, as we even started to apply that on projects, we realized we may have cases that aren't governed well by this tool. For example, I mean, while we can simulate almost any 2D rectangular window pretty well with between all the geometric inputs on the web tool, as soon as you have like a crenellated facade like what you see there, right. It may not be as good of a representation, or you may want something else. So we realized that now that we had a good sort of fast, simple, basic tool, web tool, that we can maybe now have a slower, more advanced, or able to account for more complex situations on the Grasshopper end. Okay. And that we can really tap into the 3D capabilities of the Rhino Grasshopper interface with that.
So as you're saying, the big idea here is in the original tool, you're assuming you just got a flat, straightforward facade with a really simple window that's being repeated all over the place, and that's your study. But here you're saying, well, a lot of buildings aren't that simple, and so here's a way to handle those situations.
Yeah, and it could even be one building, but maybe you want something really early in design that's kind of quick, just rules, not rules of thumb, but kind of quick early numbers as targets, and then as you develop the design, you want to get more into the details, and so you can kind of have a quick early one versus a more detailed one for design development.
Okay. And so you can come up with, the idea is you get a general strategy. You can say, all right, I know we need to do punched windows if we're going to have double glazed, if I want to be able to remove perimeter heat. You can do that quickly with the web tool and find that out for your climate. Okay. And the other one is not really meant to do the fast iterative stuff. It takes 30 seconds to run, but it can handle a whole bunch of other types of situations.
Okay.
And so so we had the idea also with this dual support, this dichotomy that we'd have basic quickly toggleable inputs for everything on the web tool that were easy to change things around. And the Grasshopper tool would be, for those of you who know Grasshopper, it's component based. And so that allows, it's a set of functions that are each wrapped in their own little component that has inputs and outputs. And this allows you a lot of flexibility. So for example, if we wanted to take results from an energy model and plug them into our tool, you could do that with these components by plugging those into the right input. Or if you wanted to visualize different outputs in a different way, it just allowed this flexibility that you wouldn't necessarily as easily be able to get with the web tool.
Okay.
And also
I like the ankle draft discomfort components.
Yeah. Yep. Those are all, by the way, components that we made for the tool and that are now part of Ladybug.
So when you download Ladybug, they come. Yeah,
that you can get these yourselves and mix and match them to solve other problems that we haven't thought of yet.
That's awesome. David Rutten never knew that there would be a component called the ankle draft.
The ankle draft discomfort component. Yeah, speaking of bad names of the tool, some of my components are like,
That's really funny.
the shade benefit evaluator, it's like,
That's awesome.
Anyway, but I gotta hire someone to figure out better names.
Those would all make great T-shirts, but anyways.
All right, so and the idea also with this dichotomy, we'd have like JavaScript would be the main thing that's under the web tool. That's the code under the hood. And for that, we're borrowing a lot from the center of the built environment. We're actually taking their comfort functions and using those in our web tool. And that's also another reason why it's open source, because their web tool was open source to begin with, and so now we're building off of that. So I mean, we now give that back, as under the same open source license. And similarly, and so you can actually, we want it to be very accessible if you did want to look into the code. So in your web browser, you can check it on the web tool. And the components on the Grasshopper tool, you just double click on a component and the code pops up. It's all within there. And we're building off of Ladybug's functions, as I kind of already mentioned. Some of those open source capabilities that are already there. And some of the other differences, like whereas in the web tool, we needed a very fast geometric calculation, we're using the same thing that we did in the Excel, which was a single formula to calculate these solid angles, which then you can translate to a view factor. And it's super fast. but it has a notable limitation where it only works for rectangular windows or rectangular walls. And so as soon as you don't have that, as soon as you have a triangular or trapezoidal window or some space that's different or a surface that's going to block your view to another one, you can't really use that. And so that's why it was good for the web tool because it's very fast. But on the Grasshopper tool, we said, let's make this handle any geometry we can think of. And so we use a different method called ray tracing, where we simply project like hundreds of vectors from each and every point that we were interested in looking at comfort. And we see where those vectors intersect. And we say maybe we got 50 intersecting with this surface, 50 vectors. We divide that by the total number of vectors, and you get a view factor. And so it's much more time intensive because you're computing hundreds of intersections, but you can do any geometry. You can do geometries in front of other geometries. It's a lot more freedom, so we can handle different types of cases.
Okay.
And we did the same thing with the downdraft, that there's a simple formula or function, very quick to calculate for the web tool, that is just looking at what is the airspeed in front of the window. Whereas on the Grasshopper tool, we said, let's make this handle all different types of windows. So you can do plane intersections with the different types of varying window height windows and get different heights to plug into that formula. You can calculate the spread of the downdraft over. And all this, I know I'm getting very nerdy here into like geometry nerd land. But all of this was in the next slide was just to give us, now we can get these nice like false color maps of radiant temperature and of airspeed and of comfort, maps of comfort over the floor in percentage of people dissatisfied. For all these different geometric cases, and you can see, okay, as you go into a corner, it gets really cold because you've got two glass surfaces that you're radiating to, and et cetera, et cetera.
These diagrams here,
yeah,
PPD, percent of people
People
dissatisfied.
dissatisfied.
So those
Exactly.
are mad people.
yeah,
So more is worse.
Yes.
So
yeah, and we made them blue in the in these diagrams to indicate it's too cold, because
yes.
it's a winter comfort
it's too
tool.
cold. Got it. Okay.
And so yeah, and the red temperatures means that you're nice and comfortable
Okay.
and nice and comfortably warm.
Okay. Cool.
Yeah, and so you can see, it's still, all Grasshopper scripts are never immediately readable, but at least you can tell from our previous iterations that this was much sleeker, simpler, because we wrap things into, components dedicated components that do the functions, rather than having like 50 or 60 native math Grasshopper components to do a certain function. And we can do things like, plugging in energy model results to a Grasshopper tool. Honeybee allows you to build these full building energy models or test box energy models. So we could say, like, one of the things that immediately we were wondering, because we do a lot of radiant floors especially in like kinds of atrium spaces. And at least I was curious, how does that really mitigate the discomfort a lot? And I could take the results of an energy model and use those surface temperatures and everything from that in the tool, because it's a Grasshopper tool, and you just plug those in as inputs. And you can see it helps much more than an air system, which is the fan coil units there.
It's the one on the left.
Yeah.
Okay.
And yeah, and now that we had like a pretty robust Grasshopper tool, we had the web tool that was working. This was what I had mentioned earlier, where these scientists over at Berkeley are now like rewriting the standards for comfort. Because originally the comfort model to deal with downdraft was based on blowing cold air on the backs of people's necks, which is the most sensitive part of your body for downdrafts, for cold drafts. And they were originally doing that because they were worried that HVAC systems, they could blow cold air on the back of your necks. They wanted to make sure that no one was uncomfortable for that. But of course, it's overkill for our problem, which is just cold air going past your feet. Our backs of our necks aren't nearly as sensitive as our feet are. And so the scientists over at Berkeley said, all right, we're gonna redo this, so that we have a better way of assessing this comfort. And they you see there's a picture of their experiment in their climate chamber, which is a very nice looking climate chamber.
Yeah.
They like to brag about it, I know. But then they blew cold air around people's feet, and now have a much better comfort model. And that should hopefully be in the standards within like another couple years. But thanks to us being open, they've shared that with us now. And
Oh,
we're already,
So we're in the process of updating our tool to account for their new model.
yeah, so we have a web tool 2.0 now that has the new standards.
So
and
I guess,
concerned.
so as a result of this study, what's the result? Is it that it's easier to heat and cool
Well,
spaces, or?
The result was that we basically, because the only model that existed was using the back of the neck, we were overestimating the impact of downdraft. And so we were ending up with slightly more conservative designs than we needed to, basically. And so by incorporating their new model, it now makes that estimation more reasonable. And so some of the things that previously our model was saying, well, that might not be comfortable, actually turn out to maybe be okay. Because we were using a model that was more overly conservative.
Okay. And have you, I don't know where you are in this whole process, but you've incorporated this, now you're using it in some of your designs. Have you actually executed any designs and then gone back and sort of confirmed that, yeah, we did this, and yeah, we are seeing this?
Yeah.
Not from the, we started the tool in 2014, we started doing this research in 2014.
Mm-hmm.
So we definitely have used it in a lot of our designs that are kind of under construction and just finishing, but design takes a long time.
Oh, yeah.
So we're just right now finishing up the second version of the tool, but even the first version of the tool, we really finished this like June-ish, May, June.
Yeah.
And so we've used it in design, but obviously nothing is built and we haven't been able to measure it yet.
Okay.
Wouldn't it be great if we were done, but.
Yeah, it's okay.
Well, we do have one
Back in 2
case,
years.
one
Yeah,
validation
exactly.
case we'll show.
Yeah.
Of at least of what we had to do before we had this tool.
Yeah,
if
so
we
we've
wanted
gone
to.
back and looked at past projects to kind of say like, because previously when we wanted to look at this issue, we had to run a CFD model.
Mm-hmm.
And so we've gone back to some of the ones where we had that CFD model to say, well, how close is our tool to what the CFD model was saying, whether or not it's comfortable. So we've tried to do some validation in that sense.
Okay.
CFD being computational fluid
Yeah, sorry.
dynamics, which
Thank you.
is it's probably one of the most advanced things we do with the computer. Simulations that can take weeks to run. Anyway, we'll get to that. We'll talk about that.
We can come back and maybe do the demo in a moment.
Okay.
Do you guys want to do?
Sure, we can do the case study.
A little bit of.
So this is actually that case study. This is a project that we just finished construction. Actually, we're punch listing it right now at Northeastern University, not too far away. So if you guys want to hop on the train and go to the Orange Line, the Ruggles stop, it's right there. And it's got this curved facade of sunscreens. And then behind it is actually a pretty traditional dumb curtain wall, for lack of a better word. It's mostly all glass in the office area.
Okay.
And we had, if you go back, well, it doesn't matter actually. So we had in our design, we had a bit of miscommunication that had happened with our engineering partners for this. And so when we got to DD, we realized we basically had drawn 2 pieces of glass in our drawing. And we'd set the goal of eliminating perimeter heating. And so they hadn't put one in. And so we had this design that wasn't going to be comfortable. It's an all-glass building. It's in Boston. It's pretty shaded. And it's a double pane glazing and has no perimeter heating. And so we were like, okay, well, we were just starting design development. We're going to have to do something to rectify this. We're either going to have to add in a heating system or we're going to have to change the glass kind of budgetary-wise. And so we did an analysis where the contractor priced both options. And we did, at the time, because we didn't have this handy tool, we did a CFD model, which is, I think, the next slide. Mm-hmm. Yeah, we did the CFD model to understand, would we be comfortable kind of current design? And we had, so the blue is kind of different shades, or the different contours of uncomfortability. And so the top one here, the person sitting at the desk, about 20 to 30% of the people would be dissatisfied. So that was above we decided to use the 20% threshold for that. So that was above our threshold. We looked at it with the 30%, or with the triple glazing, and it goes down to about 10%. 10 to 20%, right on that threshold. Yep. Which is the lower. So that's with the double glaze, and that's with the triple glaze.
Okay, so here you're seeing this. Is this the threshold?
Yeah,
this one
basically.
Here?
That's the 10%, and then this one here, this lighter blue, is the 20 to 30%.
I see. So this is the 20 to 30.
Yeah.
So this.
So the person is clearly in this.
Clearly, it's going to be a problem.
Yeah, but here you've minimized it to.
Yep.
So that.
Exactly.
It's not there. Okay.
And you can see in the plan that it's really just around the kind of mullions.
Yeah. Okay.
And while this worked on this project, just so that you guys understand why don't we just do this for all projects? This CFD study, I think it was around somewhere between $10,000 and $15,000 or something. It was a long. I mean, these are really long simulations to run. There vary so many variables. You really need PhD experts.
I think we started talking about it in July or August, and we got the results in October or November.
Wow.
So we set off at the beginning of design development knowing we had this problem we needed to answer. We needed to answer it, and so they decided CFD, the computational fluid dynamics, would be the best way to do it. But it takes a long time. So in the process of it, it's not something you can do in every project. A lot of projects might be done with the design phase by the time you get that answer, in addition to the cost.
Yep.
But it's nice because we have an example we can then validate.
But it was so
again.
expensive and so on. But I mean, $10,000 to $30,000 study is a drop in the bucket for
For the
how
whole,
much of a
yeah.
project? I mean,
Oh, the budget?
Yeah.
It's
hundreds
like-
of millions of dollars or
yes,
something like
yeah.
that? Yeah.
Yeah, I mean, it's true, yeah, it's
Yeah,
true.
so-
We're nowhere
Yeah.
near the cost of what
Right,
the
yeah,
actual,
no,
well,
absolutely.
what the big thing that was at stake was, this was the project where the extra pane of glass was a tenth the cost
Yeah.
of the perimeter heating
Yeah.
system.
Because we
That
actually went
was-
and priced both of them.
Yes, it was definitely
And
worth it.
so this is using our tool. The same analysis would have taken us 3 minutes, if that. In addition to going to the triple pane, we also decided to raise the sill height of the window by a foot to kind of combat that downdraft. And so you can kind of see from the screenshots there of our tool that doesn't have the sill raise, but you can see that it went from the orange line was the previous design with the double glazing, and the blue line, which is now below the comfort line, it sort of moved it into the comfort threshold.
Okay. And again, 20 was, so here's your 20.
We were using the 20% threshold.
So that line right there.
Yeah.
So these guys, again, at, whatever,
Yeah,
less
they were
than
about
2
2
feet.
feet. Yeah,
trying to draw this sideways, but yeah.
that's okay.
Yeah, and maybe just to explain that a little bit. So with the way that the standards are being written are such that 10% is what the threshold is drawn out for full body discomfort, but they're making it a 20% dissatisfaction at the ankle level. I mean, I guess the assumption is that maybe we can tolerate our cold feet more so than we tolerate our whole bodies being
Okay.
cold.
So we just need like ankle, what are those things, leggings that used to go up to your knees
Yeah.
or something like that?
Yeah.
Office,
Yeah,
What's
bring
the
back
word?
the 80s.
because leg warmers. We need leg warmers, office leg warmers.
Which is another way you can deal with thermal comfort.
That's
You can
right.
change your clove value.
Yeah.
Or we could have everyone get up and do jumping jacks.
Those are inputs you can change if you know that they're going to happen.
I'll take that, okay.
And so, yeah, the project, that's just sort of the final facade. And we're able to execute it without having to have the heating.
Awesome.
These are just some useful links. The link to the current tool, the version 2.0 beta, where all the code's kept, and to the Center for the Built Environment and Ladybug, just because so much
We
comes
use
from
them
it.
heavily.
Yeah.
Yeah.
Awesome. We're gonna hop over and take a look at their actual tool, and you can sort of check it out. But maybe I'll see if anyone here has any questions while we're doing that. If you do, just let me know. Does anyone have any questions about this glazing and winter comfort tool these guys built, or how they built it, or why they built it? No. Cool. Well, yeah, sure.
Was potentially put like the $10,000 or $2,000 studies like those people out of a job in a way? Like will that eliminate that industry? This tool make it so easy.
Probably not, because the vast majority, it's only done very rarely anyway. So most of those people, have other things they do. And a lot of CFD studies are still being used to look at wind. We do CFD studies to look at kind of the impact of wind on the street, diffusion of, lab exhaust in the air and where it might be going. So there's a lot of uses that most of what we use CFD studies for is actually not for this. And so I don't think they're too worried about job loss.
Yeah, I mean, they
The
have,
problem is more is they weren't happening, and so most of the time we weren't making informed decisions.
Right.
yeah, those people running CFD simulations have way more advanced stuff that they could be running
Yeah.
than what we have here. They have, I mean, that's what is used to design airplanes and all these other things, as well as outdoor comfort wind simulations. A lot of really complex cases can be modeled with that. So I'm sure they're fine.
But good question. Yeah.
Do you still run into issues with clients having a hard time accepting the more upfront costs of maybe adding an extra layer of glazing even after showing them all this information?
That's an interesting question. I would say personally no, because usually their biggest concern is comfort, and so if you can prove or at least accept a tool that it's comfortable, then usually they're okay. What we've actually run into more is when they don't eliminate the perimeter heating, but for other reasons. So we have 2 projects in the office right now, one of which you need it for emergency backup. So it's a university, and they experience power loss fairly regularly, apparently. And so the rest of the HVAC system isn't on emergency power, and so they need that so that the building won't freeze, basically. And so they're putting it in with the assumption they'll never really turn it on, but then you don't get that benefit of the savings because they need it as a backup solution. So we have and then we have another project where, even though both of these projects are triple glazed, so they could very much get away without having the system. We have another project where they decided that the faculty at this university really rule everything, and they just want 0 complaints. Budget isn't a big issue, which is a very rare thing in architecture, but a great thing. And so they just kind of decided they were going to put it in anyway, just because they don't want to ever worry about complaints. And so even though we designed it, we showed it to them, they were like, we're still going to buy the permanent heating. So we've actually had more cases of that, of where even when we can prove to them they can get rid of it, they're like, it's almost like a security blanket. They don't want to get rid of it for valid reasons, but you know.
But I would imagine once you've got 3 or 4 buildings under
Yeah.
your belt that are done, and 3 or 4 clients who are going to say, yeah, we got it, and we added it in, and yeah, we never use it, they were totally right.
Yeah.
And when you get to that same
Yeah.
moment where the client has to make a decision, like, why don't you talk to
Yeah.
the doctor or whoever, and then they give them a call, and
Yeah.
like, oh yeah, we put them in, we weren't sure.
And we have a couple, as I mentioned, we had a couple projects in the past where we had used triple glazing and we're able to kind of get rid of it. And we have, I don't know, I see like 3 or 4 currently in design where we've done it. So it is becoming more common. It is. I do think people will get there, but there's a certain amount of residents
Yeah.
kind of accepting. Architecture is very slow to change.
Yeah. Well, it's good that you have these projects that are sort of
Yeah.
at this state that are probably pretty massive projects to
Yeah.
test this stuff out on for the rest of us, so to benefit from that. Other questions, guys? All right, good. Well, I want to say, I want to thank Andrea and Chris for taking some time on almost New Year's Eve and come joining us here today. I want to thank all of you guys here in Boston for joining us for our first live Super Simple. This will be posted, this will be available on the web probably in a few days. So thank you guys so much. These guys will be around if you have any questions, you want to learn how to code, or you want to learn more about building science and how to become a building scientist. Here's a couple of experts to come chat with. So thank you guys so much.